Hi everyone, my name is Vishesh, and alongside my teammate Vivek, we are here to demonstrate a simulation of our electronics project, which is an autonomous plant care system. So, in this video, we'll be sharing how we engineered the circuit architecture, how the system operates, and the logical code that runs the system. So, on to Vivek, who will be now sharing the circuit architecture.
Let's take a look at the circuit. For this simulation, we are using the an Arduino UNO R3 as our central microcontroller, while our final build is designed for an ESP32. We have chosen the UNO R3 as our primary simulation replacement because it is an industry standard for prototyping, and it is also offering a highly stable 5-volt logical environment which make it perfect for validation of our analog to digital sensor module. For our primary input, we have our soil moisture sensor. This sensor works by measuring the volumetric water content of the soil by evaluating the electrical resistance between its two conductive probes. So as the soil varies out the resistance increase, which change the input voltage signal sent to our Arduino. The Arduino has a built-in 10-bit analog to digital converter which takes the income voltage from the sensor to a pin A1 and maps it to a digital between 0 to 1023. We then use this resulting digital values in our output module, which is actually the best part of the design. A lot of standard plant monitors just give you an output as simple wet and dry B. But if you are really taking care of that of your plant, like a tulsi plant that's sitting out on a sunny balcony in Dubai or anywhere in the world, waiting until the soil is completely bone dry is usually too late. So you are really want to know when it is almost getting dry so that you can be proactive. So instead of just one alarm, we have implemented 5 LEDs over here, which are blue, green, yellow, orange, and red, which give the user the real time visual idea of the plant's health. And just in case you have missed a light, we have also added a piece of buzzer on the pin tree, which act as our absolute last resort alarm, and it only goes off if the soil is in the critical red state and desperately need water.
Alright, so now let's look at how the system operates and how the simulation works. So as Vivek said, the entire system is divided into three modules. First is the input module, which is basically the soil moisture sensor. This is directly connected to the Arduino, and basically the sensor takes in analog values of the moisture levels and then sends those values to the Arduino, with which its inbuilt analog to digital converter converts those values to digital values, with the highest value in our system being 872. So the range of digital values we are going to achieve is from 0 to 872. Then this data is passed to the processing module. That's where the code logic evaluates the hydration levels against our preset thresholds. And then finally the output module, which consists of 5 LEDs and one piezo buzzer, receives the commands to provide the user with the visual and audible feedback. So now let's start the simulation and look how it works. So as you can see, as soon as I started the simulation, the piezo buzzer and the red LED light lit up, and that was because the default value of the moisture level is set to 0. So which indicates that the soil is completely dry and needs watering immediately. Then after the threshold value of 200 is reached, and beyond that the different LED lights light up. So first is the orange light which lights up, then the yellow, then the green, and then the blue. So now let's look at the code which operates the entire system. So at the very top, we have declared our variables moisture to 0, sensor power to 13, sensor signal to A1, and buzzer to 7. So basically, these values are the pins which we have connected individual tasks to. And then let's look into the setup function. So in the setup function, we have configured the inputs and outputs according to the pins. And the most important line over here is this. So this basically makes sure that the sensor power is set to off by default when the system boots up. And then let's look at the main loop function. So in this function, we have mainly tackled the important challenges which we faced. The first being oxidation. So in order to battle oxidation, what we did over here is that we are only applying power when it is needed. So when the loop function is being run, the first the power is set to on or high for the sensor, and then we wait for the sensor to stabilize. So that means we give it a 10 millisecond delay, and then after we have got our readings, we immediately cut the power off. So this prevents electrolysis and stops the probes from rusting. And so the next challenge which we faced was that we got a lot of jumpy readings in our signal values. So basically, we've got a lot of noise in our readings, and that's usually normal because these analog sensors are extremely sensitive. And so that's why we added some lines of code over here, which is basically allowing us to do a process called data smoothing. So instead of just taking in one reading and saying that's it, what we did is we created a for loop over here. And with the for loop, we taken 5 readings in a second. uh, provide a delay of 2 milliseconds just so that there's a tiny gap between the readings, and then we calculate the average of those values and assign that to the moisture value. So what this does is it does not provide us fluctuated values and allows us to find the real-time data uh, according to the moisture level in the soil. So after that, we print the smoothed average value to the serial monitor. And then after that, we reset the LEDs and the buzzer to low to clear the previous values and the state of the LEDs and buzzer. And then finally, we reach the decision making part of the code, where once the Arduino has smoothed average values of the moisture levels, it then passes that data through through this if conditions, where we have already preset the threshold values. So it first starts off by checking if the moisture level is less than 200, which means that the soil is completely dry and it's in a critical zone. So according to that, it sets the red LED light on, and it sets the buzzer on. So then accordingly to the threshold values which it has checked, it sets off the individual LED lights on. Now let's look at the serial monitor once we run the simulation. So you can see over here, as I started the simulation, the moisture level, the readings which we are getting are 0, which means that the soil is completely dry and requires watering. And according to that, it even turned on the red And so when I slide up the moisture level, you can see the moisture level readings also increase, with the highest value being 872. And so this proves the efficiency of the project and the agenda of the project is fulfilled.